Hi, this is Dr. Viv, and I will be discussing the half-tangent substitution. It's one of those things that fall by the wayside of a first course in calculus because the instructor runs out of time, they have to teach so many other things, and then you never learn it again because you move on to more advanced things. So it's one of those twilight zone casualties. Instead of solving the actual problem here, which is integral d theta over 3 plus 5 cosine theta, I'll do something more general. I'll call this some integral I as a function of a and b is equal to the integral of d theta over a plus b cosine theta. I have to mention that I can have sine as well. This substitution works for either sine or cosine here. So the substitution in question is called a half-tangent substitution because that's what it is. Z equals tan theta divided by 2. Now when you have something like this, I can immediately find what dz is. It's 1/2 secant squared theta over 2 d theta. But secant squared theta can be written in terms of tan squared theta as follows. So dz can be written as 1/2 1 plus tan squared theta over 2 d theta, and now I can substitute back what z is. So this gives me dz equals 1/2 1 plus z squared d theta. Once I have that, I can write down what d theta is because my aim is to get rid of theta. So d theta will be equal to 2 times dz divided by 1 plus z squared. So that's the first result. It seems like I've traded something simple, which is d theta, for something more complicated, but wait and see. The whole thing will be very simple once we finish. Cosine theta, what's cosine theta? Now I'm going to use the identity known as the half angle identity. Cosine theta is cosine squared theta over 2 minus sine squared theta over 2. But I have tan theta. I don't have cosine or sine theta over 2. So what I'm going to do is I'm going to make this happen by substituting, by taking as common cosine squared theta. Then I get 1 minus sine squared theta over cosine squared theta, which is tan squared theta over 2. Now cosine squared theta I can write as 1 over secant squared theta, and I'm back to business there. So this is 1 minus tan squared theta over 2 divided by secant squared theta in the denominator, which can be written as 1 plus tan squared theta over 2. So I have a nice expression for cosine theta, and that is cosine theta is equal to 1 minus z squared over 1 plus z squared. Now I said that integral could also be sine theta, so let me go ahead and give you what sine theta is in this scheme. Even though there are two options, you can either put what sine theta is, or if you want, you can change theta to pi by 2 minus theta, do a first u substitution and change theta to pi by 2 minus theta, and then change sine theta to cosine theta, and then proceed with this method. So you can use either of those two techniques. But let me write sine theta anyway. Sine theta in the half angle formula is 2 sine theta over 2 cosine theta over 2. And once again, I'll play the same trick. I'll multiply and divide by cosine theta. If I divide by cosine theta, that gives me 2 tan theta over 2. And then I have to also multiply by cosine theta over 2, so that gives me cosine squared theta over 2. But cosine squared in the numerator is the same as secant squared in the denominator, so that's going to be 2 tan theta over 2, and secant squared in the denominator can be written as 1 plus tan squared theta over 2. So that also is a nice result, and that tells you all factors of sine theta can be written as 2z over 1 plus z squared. Once you have these, you can go back to your original integral and substitute these things. So let me go over to I of a comma b. That is the integral of d theta, which I can write as 2 dz over 1 plus z squared divided by all this here. So that's a plus b times cosine theta, which is 1 minus z squared over 1 plus z squared. Now you notice that 1 plus z squared will cancel out, so I can rewrite this as follows. Two dz divided by a times 1 plus z squared plus b times 1 minus z squared. One more step, let me take all the constant terms together in the denominator. So that gives me 2 dz divided by a plus b plus a minus b times z squared. Now if you observe that substitution z equals tan theta over 2, there's this factor of a minus b which we need to get rid of. If I just had 1 plus z squared, I can make another substitution, another tan substitution, and take care of this integral, but this factor of a minus b is bothersome. Now here there's a contest. Is a bigger than b or b bigger than a? So let's take the two possibilities and examine each one in turn. So the first possibility is that a is bigger than b. If a is bigger than b, that's going to be something like 1 plus z squared. So you're going to have a tan substitution. So what I'll do is I'll say z equals the square root of a plus b over a minus b tan of some other angle. I cannot use theta anymore, so I'll use the angle psi. If I use the substitution, observe that when I take z squared, I get a plus b over a minus b, and that a minus b cancels out nicely, and I just get a plus b common in the denominator, which I can pull out. So this will work out nicely. Take the dz of both sides. So that's going to be a plus b over a minus b times the differential of tan, which is secant squared psi d psi. Let's substitute this back into the integral. The integral gives me two times the square root of a plus b divided by the square root of a minus b secant squared psi d psi divided by all the other things. So there's a plus b plus, and here as I said, if I square this, the a minus b's will cancel out and I'll just get another a plus b tan squared psi. Now this is a plus b times 1 plus tan squared psi, but 1 plus tan squared psi is the same as secant squared psi. So I can cancel those two things out, and I very simply have evaluated the answer. One of the factors of a plus b in the denominator will cancel out the square root of a plus b there. So let me take a step to indicate that. And here I'm just going to get the integral of secant squared psi d psi divided by 1 plus tan squared psi. And as I said, those two things are the same. And here, once I take the cancel out the square roots, I'll get a plus b to the power half. Now square root of a plus b times a minus b is a squared minus b squared. So that is just going to be 2 over the square root of a squared minus b squared, which is real because a is bigger than b, times the integral of d psi, which is just psi, plus some constant c. in this way we have solved the problem. Now let's take a moment to back substitute everything. So psi is given by the arctangent of all that. So this is going to be an interesting process. So it's going to be 2 over the square root of a squared minus b squared times the arctangent of this huge thing. So now when I move it to the other side, I get the a minus b above. Okay, of z plus c. Well, the story is not finished because now z has to be resubstituted. So this is going to be 2 over the square root of a squared minus b squared tan inverse of the square root of a minus b over a plus b, and z itself is tan theta over 2 plus c. In this way we have solved this integral. It's a magnificent result. And not one that you could have done by any other means. It's quite a tricky integral, and you cannot just do this using the standard tricks of calculus that you may have learned. Now, what if a were not bigger than b but less than b? So let's address that case. If a is less than b, then you're going to have a negative sign there. So I can write this as follows. I can write I of a comma b as the integral of 2 dz divided by a plus b, and I can put the negative sign outside so as to guarantee that whatever is left over is positive, and whatever is left over is b minus a. And since a is less than b, or in other words b is bigger than a, b minus a is always positive. Okay, now I can make a u substitution, and that u substitution is the following. It's a square root of a plus b over b minus a. So just as I had the z substitution there in terms of psi, I'm having a u substitution here times z. That's it. If I put this back here, I should have written, I think, z equals the whole thing times u. That's what I wanted to do. Okay, so sorry about that. If I square z, then the b minus a will cancel out, a plus b will appear outside, and everything will be good. So let me do the substitution. Therefore, the integral ab becomes, when I take the dz of this, that's just going to be du times all this. So 2 root a plus b over b minus a times du, and the denominator will become a plus b minus, and I take the square of this, I'll lose the b minus a and I'll get a plus b again, u squared. Now that's a very simple integral. Once again, I'll have this a plus b common, and that'll cancel out the a plus b there, so I'm going to get 2 divided by, instead of a squared minus b squared, I'll end up getting b squared minus a squared. And that'll be the integral of du over 1 minus u squared. Well, that is easy to do by partial fractions. So this is just going to be 2 over square root of b squared minus a squared. And let me do this by partial fraction decomposition. The answer is actually simple enough to just guess. The denominator is 1 plus u times 1 minus u. So I can write this as 1 minus u. I don't know if it's plus or minus, so I'll keep that as an unknown, 1 plus u. Now let's see what happens. I need a 1 in the numerator, so if I do this, it's 1 minus 1 plus u there and 1 minus u there, so the u needs to cancel out, so I'll get a plus. Now let's see, it's 1 plus u plus 1 minus u, the u's cancel out, and that's 1 squared minus u squared, or 1 minus u squared, but I have a 2 there because 1 plus u times plus 1 minus u is 2, so I'll have to make this a 4. Well, I have to compensate it by dividing by 2, and so these 2's cancel out, and now I'm just left with du, and so the answer is 1 over the square root of b squared minus a squared times the natural log of the absolute value of, this gives me the natural log of 1 plus u, and that gives me negative natural log of 1 minus u, and that negative natural log can go in the denominator, so that's natural log of 1 plus u over 1 minus u plus c. Now I'll let you have the fun of unwinding this expression, so take a moment after this video to put u in terms of z and put z in terms of tan theta over 2. So we have solved this integral for all possible cases of a and b.